to be hearing about Titan and the storms and lakes and methane cycle on Titan. The speaker will be Dr. Caitlin Griffith. Caitlin got her bachelor's at Johns Hopkins, her PhD at State University of New York at Stony Brook, and has been at LPL for 15 years, something like that, roughly, and is now a professor of planetary science here. So without further ado, one other thing I have to say. Sorry. One other thing I have to say, if you are attending for a class and need to get your notes initialed or something, they will be doing that in the back after the talk. And whether you're attending a class or not, you should stick around because there's a raffle. So without further ado.
Okay. Cheers, everyone. So we're going to be talking about Titan, and I've made a very long title, I see, but basically it lured me, and I'm hoping that the questions that come up are very luring to you, but we'll see if that works. So I was kind of inspired last week by the takeoff of OSIRIS-REx and about how everything works, starting from the beginnings of an idea of a spacecraft and ending up to a takeoff and then ending up to a long mission. So I'm actually going to take this in exactly that kind of way. I'm going to start out with an introduction that discusses what we thought Titan was like before Cassini. What were the main questions? Why Titan? It's only a moon, right? It's not even a big planet or anything like that. And then I'm going to talk about what we found. You know, were we right? Were we wrong? You know, how well did we get there? And then I'm going to talk about where we are now, which is, does it make sense? What we learned from Titan, does it really make sense? In some ways, it doesn't at all. We're still in that stage. And then you can always ask the question. This is a question that's being asked both on our side of the Atlantic and on the European side of the Atlantic. Should we go back? Is it a pressing thing? Is it interesting enough that we should go back? Are there enough interesting questions that we should approach? So first of all, start out very, very basic. You know, why Titan? Well, first of all, it's an oddball. If you look at the moons that surround Jupiter, and they're the same size as Titan, the same density as Titan, and presumably, because they have the same density, you know, maybe they're made of the same material. But as you can see, and as probably most of you know, there's only one of them that has an atmosphere. And it's a thick atmosphere, as you can tell there, but you can't see anything but this hazy planet. And then you could say, okay, let's compare Titan not only to moons, but let's compare them to the rest of the guys in the solar system. And you could say, okay, the way I like to put it is, where's the best place for a picnic? Would you go to Jupiter for a picnic? No. Why not? Because it doesn't even have a surface. So you would end up going there and you end up getting squished to death, bad picnic. The same is true with Saturn, Uranus, and Neptune. That would be a complete disaster. And you might want there to be an atmosphere. So then that leaves out Mercury. Mercury has an atmosphere that's way too small to even think about. It's not. And then you're left with Venus. Where's my stick? Oh. You're left with Venus, Earth, of course, you know, and Mars. And then, of course, I put this in here, and Titan. So if you want to be interested, if you want to look and study planetary bodies that have atmospheres, significant atmospheres, have surfaces, because of course Jupiter has a significant atmosphere, it just doesn't have a surface, then you're kind of stuck with looking at these guys right here. Let's see, how do we advance this? I've done this before. Okay, yeah. And these are the ones we've been to before. This is, well, this one you know, right here. It has real estate, coastal real estate. And then this one, of course, you know, because it's next to the Earth. So it's Moon, Venus, and then we have Mars here. And before Cassini went to Titan, there was Titan as well. But it was the only other planetary body which has an atmosphere, has a surface, that we hadn't been to before. So that's one interesting thing about it. Now let's compare a little bit what what these guys are like. So here's planets with atmospheres and surfaces. Yep. And what are these atmospheres like? Well, they're all entirely different. And here I've listed the pressure in terms of atmospheres. So Earth would be 1. And then this U is called the calm abundance. That's what is the density if you integrated it above your head? So how thick is the atmosphere? So this gives you an idea of what the size of the atmosphere is, and then, of course, the temperature, and the temperatures in Fahrenheit. And you can see that Mars, excuse me. Mars has a very, very wimpy atmosphere. It's got an atmosphere with a pressure, and I've rounded these up a little bit, a pressure of 0.01 atmospheres. It actually varies quite a bit. And it has this calm abundance or the amount of atmosphere it has is 100th of what Earth has. So it really is a very, very thin atmosphere. Now the temperature is okay, but it actually varies quite a bit. It varies between about let's see, what was it? It gets down to minus 200, actually, but that's rare in the poles. And it gets pretty high up. Wait, what's it low? It's not that low.
Cold is carbon dioxide, right?
Yeah. Let's see, let me think about it. We'll get back to that. It gets very cold, and it gets pretty temperate as well when you get up to there. Because what I've done is I've mixed things up because this, let's leave that. But when we get down to Venus, we find that it has an enormous atmosphere. It's an atmosphere that's 500, so it's going to be 50 times the thickness of Earth. It has a pressure that's 100 times the pressure of Earth, and that pressure is actually similar to the pressure you would feel if you actually went scuba diving and you scuba dived down to about 1 kilometer under the ocean. Then you would be experiencing the same pressures that you would be experiencing on the surface of Venus. So it's not a comfortable place. Now you get to Titan, the pressure is basically about the same as the pressure on Earth, but the amount of atmosphere above the surface is quite a bit larger, and it's basically 10 times larger. And the temperatures, this is in Fahrenheit, are very cold. So they're all quite different. Yeah?
Where on Earth does it get up to be 285?
You've got Fahrenheit and Kelvin.
I got Fahrenheit and Kelvin mixed up.
Oh, okay. So
That's what I was going on. So this is actually in Kelvin right here.
Kelvin for Titan?
No, this for Kelvin this would be 90 Kelvin actually. So I got those a little bit mixed up. You can look it up, but let's see. And in Kelvin this would be 720. So it's quite a lot. And let's see. And then Mars, and this is Earth, and you can see Earth is in Kelvin, and you can see that Earth should be something like, 58 degrees Fahrenheit, and then Mars should be a little bit less than that. But the Mars temperature changes a lot because the atmosphere is very thin. Okay, yeah, sorry about that unit problems. You should always tell the students, you shouldn't mess up your units, and here we are doing it over here. But I'm a professor, so I can do that. It stimulates. Okay, now, so it's interesting because it has an atmosphere, but it also has an atmosphere that's in some ways very interesting because it has a constituent. The main constituent is the same as the main constituent on Earth. So the atmosphere is basically nitrogen-based, like Earth. And it also has methane in the atmosphere. And methane is interesting, too, because it's in the Earth, but it's not a very abundant element in the Earth. But in the past, based on geological records and based on models of Earth's atmosphere in the past, there are some models that indicate that maybe Earth had a lot of methane in the past and doesn't anymore. And so one idea for going to Titan was actually to explore models of early Earth. The question is, what kind of an atmosphere would we have if we had an atmosphere of nitrogen and methane, and how would that atmosphere, what could it tell us about Earth? And you might say, well, this is kind of far-fetched because Titan is really very, very cold. But actually, we did learn something about this, and this will come up a little bit later in the talk. But we didn't go in there blind. We knew that there was methane in there, and we knew also that there were other organic material in Titan. And this is from ground-based observations using telescopes and spectrometers. I won't go too much into that. But we knew that there was ethane in the atmosphere, too. And we knew that there was a whole bunch of compounds that are organic. And by organic, I mean compounds that have carbon in them. And it was realized that maybe what we're looking at is a situation where this moon has quite a bit of methane. And this was actually, there were very interesting spectra taken by Larson and Fink, and they were here in this department. And it found that there's quite a bit of methane in the atmosphere. And Jonathan Lenine, who was also in this department at the time, he came up with this model for Titan. And the model was this, that first of all, he realized, as did others, that these other species that were being found, especially the ones with carbon in them, in Titan's atmosphere, they're actually formed by methane. And essentially methane, and here's methane, it has a carbon atom, and it has 4 hydrogen atoms, and they're bonded by just a single bond in each case, single bond. So it's very easy to break this molecule apart. And once you break it apart, and it's broken apart by UV radiation, comes to the top of the atmosphere, it breaks into little bits like CH2, CH3, and those are very reactive radicals. We call them radicals. It sounds great. And they react together, and they make mainly ethane and a whole slew of other things. So it was realized that probably, since Titan has methane, it probably has a lot of organic material, which was interesting. And Jonathan came up with this idea that maybe what we're seeing is we're seeing methane being broken up. It has to be being broken up because we're seeing the byproducts. And what's happening is that these byproducts are making that hazy atmosphere, which is just a bunch of organic material. And it's also making the ethane. And it's mainly making the ethane. And this ethane will mix down to the lower atmosphere. And at the temperature of the lower atmosphere, at the surface, ethane is a liquid. So basically his idea is that, okay, this is an atmosphere that's changing. It's a moving atmosphere where you're depleting the methane, and you're making mainly ethane and haze and all this stuff, but mainly ethane, and that's mixing down, and then you're making like pools of ethane on the surface. Now, methane also is liquid on the surface, so he had this idea that you have pools of methane and ethane. And do any of you know what methane and ethane is? Do we deal with methane and ethane? The students? It's natural gas. So this is a concoction of natural gas. This is a planetary body that's full of natural gas, and kind of changing the constituents of the natural gas. There's natural gas. Methane is a natural gas, so is ethane, and it's kind of changing the methane into ethane and a whole bunch of other organic materials. And all this stuff, including the haze, this is hydrogen cyanide, very poisonous, and this over here, all that's just eventually ending up in the surface and making sediments of organics on the surface. So it's an organic gook, planetary atmosphere surface. So, and then they decide, okay, well, this is happening very quickly, so if Titan has had if it's had methane over its lifetime, that's 4.5 billion years, if it's had methane, it's got to have had a lot of methane because it's using it all. And it's got to have a lot of ethane falling down to the surface. And you do the math, and he found out, well, you have to have basically between half a kilometer and a kilometer of some methane and ethane at least. And this is a kilometer if you just assume that it's a uniform layer of ethane and methane. So a lot. You have to have a lot of this stuff. And so this led Jonathan and Carl Sagan actually wrote a paper about this. And the idea was that this is an ocean planet. This is a planet that has an ocean, because it has to have a lot of this stuff just to supply the methane. And it's actually pretty much covered with methane and ethane. And part of the reason why they thought that it was just another point is they thought that it was completely globally covered is because Titan has a very large inclination in its orbit. So if it goes around Saturn, it has an inclination. It's not a circular orbit. It's an inclined orbit. And the idea was that if you had a whole bunch of continents, that would dampen the orbit to a circular orbit. That was the idea at the time. So this is what we thought Titan might be like when we got there. Okay, so now I'm going to talk about the Cassini mission. And it was $3 billion. And those were in $1 billion in the past, so it's a bit more now. But it has a lot of instruments, 12 instruments on Cassini. And it also had a probe, which is to detach from Cassini, the big spacecraft, and actually go down to the surface of Titan. And that's right here. It looks like a shield here. And look how big it is. It's quite big. See, these people are not kids. So it's about 30 feet. And I'm going to be talking a lot about radar observations, but I'm also going to be talking a lot about observations that were made by instruments that were developed and built here. And one was built by Marty Tomasco, and it's on the probe that landed on Titan. And it basically takes images of the surface. Any images you've seen of Titan's surface came from this called DISR instrument. And in fact, there's a number of people in this audience that are on the team. And would you mind raising your hands, please? Because there are a number of you. Okay, and this is a team effort because the person that's in charge has to do things like buy light bulbs and things like that. And they don't have time to do all of the science, so you have to have a very tight group. And in fact, that story does come up. They were running short, correct me if I'm incorrect here. They were running short on funds, and they needed a lamp because they're going to land on the surface, and you want a lamp, right? You want to turn on the lamp and look and see what's on the surface when you get there through all the haze. So they needed to buy a lamp. They came out with a bid, and it was $2 million, as I understand. And they didn't have the money. So they basically went around and looked for light bulbs, essentially, off the shelf, and tested them to see if they could survive the Titan IV rocket. And that means basically jiggle them a lot. And one of them worked, passed the test, and so they just used something off the shelf. They were going to the stores and everything. So you have to think out of the box when you're doing these. And another instrument was built here, and this instrument was actually on Cassini. So it's currently orbiting around Saturn, passing by Titan still. And that was designed by Bob Brown here. And that also has an imager, but it's an imager that's much better than our eyes because each pixel is a spectrum. So it's not just average. When we look at things, we look at this. This is orange because it's kind of average orange. But I don't know how much green light there is in here. I don't know how much blue light there is in here because my eyes just average the thing, and it just says orange to me. But imagine if you had eyes or if you had an instrument where when you look at every single thing, it would tell you not the average light color that's coming there, but little, just in detail, how much there is of every wavelength. So that's what both of their instruments do. In fact, they're spectrometers. So this is a joint. Another important aspect about this is that this is not only a huge mission, but it was a joint effort with NASA and the European Space Agency. And it worked out beautifully. So here's the European Space Agency built the probe that landed on Titan. And here it is, and you can see it's got its tiles to protect it from the heat during entry. So as we know, it worked out very well. The blast off, there it is. And actually, there was fuel to spare, so that was quite nice. And there was a waiting period because they had to go pretty far, right? So you have to get to Saturn. You know, they went twice around the sun here, and then they went all the way out here. It took about 7 years. And during that 7 years, all of us were trying to figure out what was going on and what we would see. During that time, I got very, very interested in the question of whether we could see the surface and whether we could see all this organic gunk on the surface and what could we tell about it. And so I figured out a way of doing this that would get me to Hawaii for 2 weeks. Basically, the idea is very simple. It's essentially what you do is we knew at the time that like the moon, the way the moon goes around the Earth, that it always has one side pointing towards the Earth. Now, Titan is the same way. So it always had, we expected it to be the same way. And it always has one side that's facing Saturn. So imagine this is Saturn, this is now Titan, okay? So the idea is to just take a telescope in Hawaii and then just look at it. And when you look at Titan on this side, you're looking at this side of the planet. And when you're looking at it at this side, you're looking at the other side of the planet. And if it isn't a planet that's completely covered with liquid, that is uniform, you would expect to see some variation that's reproducible in the light that's reflected off of Titan. So you would expect to be able to see the light that's reflected off of Titan. It would be different probably here because probably there'd be a different amount of dark and bright stuff. And so it takes 2 weeks to go around, so you have to hang out in Hawaii for 2 weeks. And then you have to do it again to see if it's reproducible. It's terrible. And yeah, at least twice, right? And you do find that it is reproducible. You do find that if you're looking at a certain longitude, you do find that you get the same curve many times. You can do it many times. I was only able to do it twice. And then you get the same curve too. But you also get, on one night, you get these weird ones right here. And this is actually another reason why I was going there, because I wanted to know whether there were clouds also on Titan. And why did I want to know? Because we know that methane is a liquid on the surface. And so maybe it has clouds, maybe it has rain. You know, it could be just really crazy having all this stuff, just like Earth. And so we found these, and we started finding them in a reproducible way. And the spectra looked like clouds, so we proposed the idea that Titan not only has maybe oceans of methane, but also has clouds going around, pretty big clouds. These clouds would have to be the size of a hurricane, in fact, on Earth, about 1,000 kilometers side. And that was heavily debated. Most people didn't actually think that was the case, which is interesting. Okay, so Cassini arrives, and we don't know what we're gonna see. And the first images were really actually kind of disappointing. First images indicated, wait, we don't see any evidence of liquid. I mean, we see this kind of dark and light stuff, which completely agrees with the little experiment I was doing in Hawaii, but we don't see any evidence necessarily of liquid, because we could even see in here, if we looked at the data very carefully, we could see that this is not just purely dark or anything like this. This actually has a lot of structure. So this was a little bit of a letdown, actually, to be honest. But then a few months later, so this is in 2005, the probe landed. And a little bit about the probe, landing a probe. So this is in January 14, and it landed. And it's interesting because what you have to do, first of all, you have this shield that protects it against the heat as it's coming down. Because obviously, you have the good thing on Titan that you have a lot of atmosphere to slow down the probe, right? But as it slows down, obviously it heats up, so you have to be worried about the heating. And there was a period of time right before this happened that we were worried that we didn't get the chemistry right in the upper atmosphere, and the heating would be greater than we thought it would be, and it sent a bunch of us actually to the telescopes to try to figure out what actually was the organic constituents of the atmosphere. But it actually worked out fine. So it came down, and actually 3 parachutes were used. So one parachute was used in such a way that it's basically made out of material that's pretty heat resistant. So you got to slow it down a little bit. And then you bring out the main chute, which does most of the slowing down. And then you want a smaller chute when you get down to the bottom. And so then a smaller chute was deployed. And I was always nervous as to whether this would actually work, all of these different things. And it did, obviously. Now, the first image was amazing. We were all in Germany, and the Germans gave us a white cloth dinner. And meanwhile, the people that were working on the images of the probe, that is, people sitting here in the 3rd row, they were in a small room, and they were collecting the data while the rest of us were upstairs with these white cloth tables and the wine and everything like that. And they said, well, look, it's only going to take us, I don't know, within an hour, we should have an image for you. And they've downloaded the data. We should have an image for you in an hour. And we thought that's probably unlikely. And you guys probably have more stories about what it was like in the dungeons there while we were sitting there. And then they did have it within an hour, if I remember correctly. And they put this up. And we thought, they're kidding us. This isn't Titan. This is Mars. And so, in fact, at my table, there was Toby Owen, one of the 3 people that put together the Cassini mission from the very beginning, and Le Béton, who was in charge of the probe. They all thought it was Mars, too. So I said, OK, I'll go down and I'll check and see if it's Titan or Mars. So I did, and it was Titan. And this is the coolest thing to have it be Titan, because look at it. It tells you so much information. It tells you that you have these boulders, these stones that are rounded. So you can imagine that probably what we're seeing is something that rolled down some river and was rounded as it rolled down. And not only that, you can see these paths here that suggested that at some point maybe there was a flow of liquid on the surface. And you can see that it gouged out this under region right here of this boulder. So this was just absolutely amazing. It's one of these moments that you can't possibly forget. And in fact, after this, I just went and wrote poetry. It's just amazing, just amazing. It gets better even yet. So here's what I'm talking about. So here, okay, we know these guys right here. Here's Mars, and here's Titan now. And if we look at it, though, in a little bit more detail, this is not quite as cleaned up, but you can see that on Mars things are really quite different. You're not finding the same thing in this particular spot on Mars, but there's quite a big difference here. I don't know if there's any other part on Mars that actually looks nice like this. It has all these boulders going around. And now, here we have to understand that the liquid would have to be methane, and that these boulders are ice instead of silicate. But it tells you there's a world out there that's so similar in processes to Earth. And it even got better. So then the next image that came across is this. It's fantastic. You have the highlands here, and you have drainages that come down. And if you look at the drainages, they're basically drainages that indicate that methane, not water, but methane that is rained down, and it's following basically the shortest path from where it is. It's a very comprehensive drainage system that suggests that it was made from rain. So that was incredible. And then this, I don't know, looks like LA or something like that, but there's like, these aren't roads here, but these are thoughts by some people to be something like slot canyons. But this here you have the drainage region as well. And then this you have flow features. So you could say, okay, that's interesting, but what is the context? This is a small area where the probe landed. It's minus 10 latitude, that is 10 degrees south latitude, and the longitude is 191 west longitude. But what do the surroundings look like? So let's look at that. This is an image taken by Cassini radar. These are dunes. All these linear things are dunes. These are dunes over here, dunes over here. And Larry Soderboom was able to find out where in the map of the radar map, where the probe landed by superimposing the images made by the probe onto the image made by the radar. Here he is superimposing it. That works. And you find that we landed right here, kind of close to these dune fields, in the middle of these dune fields, which is, my goodness, what is that trying to tell us? And then here you are, and we're right about there. And so this is sitting in the middle of a dune field, and yet, where the probe landed is in this channel that has walls that are essentially 10-meter high. So obviously there was a lot of liquid flowing down here, somehow carving that. So we didn't know what's going on here. But let's put it in scientific, or let's be rational. No liquid, but evidence for strong liquid flow. So that's what take from that. But let's look at the poles now. That was in the tropics. We look at the poles. So we're going to look again at radar observations, and these are not passive observations. They actually send a signal at this gigahertz, and then it bounces off the surface and it comes back. And this is what we see at the poles, the North Pole. We see liquid. So these are lakes, and this is about the size of the big island in Hawaii, and these are lakes right over here. To show you a few more, this is an artist's view of trying to give you an idea, because we do have some altimetry measurements as well from radar. And here again, here's another you can see drainage features in here, just absolutely beautiful. And then you can also see still the North Pole looking around. You can see these little lakes, and then you can see regions where it looks like there was probably lakes there, but they dried out. So you see evidence of evaporation, all the things that you see basically on Earth. And here's a final map of the North Pole. I don't know if this is going to be covered at all, but you can see these lakes. And there's more lakes actually in the North Pole than there is in the South Pole. Here's the South Pole. There's this lake right here, Lake Ontario, what we call it. And then there's a few other lake-like things, but there's quite a bit less here. And this is understood by looking into the temperature changes in the poles. They're quite different because there's the eccentric orbit. And so you would expect much more evaporation from this pole, given the current configuration of the orbit. It makes a bit of sense. So from this, we see that there's lakes only at the poles. Now we go to the clouds. Clouds were detected, and actually they were first detected by ground, not by Cassini. And we find that there's also a lot of organization with the clouds. Now the clouds, you see them only in the summer polar region. So here it's summer in the south, and we're headed towards summer in the north right now, and now we see clouds over there. So, and then when it's equinox, we see a few clouds in the tropics. So essentially, what we're finding is that the clouds follow the latitude of highest insolation. So let's look at Earth's clouds, see if we can understand what we're looking at here for Titan. For Earth, you find that the largest cloud abundance, first if you just look at it like this, it looks like a mess. But if actually you integrate over the clouds over, here it's done over a number of years, 1983 to 1990, then you find that most clouds are actually occur in regions of upwelling. And so we have these Hadley cells, and so you have upwelling at the equator, and so you see a bunch of clouds right there. And then you also have upwelling over here, so you see clouds right here and clouds right there. So basically, in the latitudes where you have upwelling drafts, according to the circulation. Well, it turns out that Titan has a completely different circulation from Earth. And it's actually the circulation that we would expect for Titan, because Titan spins very slowly. And because of that, it doesn't have the same kind of Hadley cells. It has Hadley cells that go all the way, basically, from pole to pole, because there's a very slow spin. And we find that actually the clouds on Titan follow the regions of higher upwelling, of largest upwelling. So in the summer, where there's upwelling here because there's heating and there's upwelling, you get clouds over here. And then when you get to the equinox, then you get upwelling over here, and that's where you see a few clouds. And then now we're in the north period where the north is summer, and that's where you see the upwelling. So it's actually the same, really completely consistent with what you would expect from Earth if you just took Earth and you just dampen the spin, so it didn't spin once a day, but spin once every 15 days. And then if you load it up with a very thick atmosphere too, you have to do that as well, then you'd expect to get this actually. So we find that this really does make a lot of sense. For both Titan and Earth, clouds form in the regions with strong upwelling. Okay, let's look at the haze. Now the haze has been a pain in the neck because it limits our view of the surface, and it's very hard to quantify. But it's interesting because the haze is basically the byproducts of breaking up methane and nitrogen. And so you have methane, nitrogen, and there's a little bit of oxygen that also comes in through comets. So you have carbon, you have nitrogen, you have oxygen, hydrogen, kind of the ingredients for life, right? And so, it's broken apart, and depending on what part of the atmosphere, a different and continuous chemistry occurs. So for example, cosmic rays get all the way down to about 50 kilometers above the surface, and that affects the composition of the haze. But it starts out in the ionosphere. It starts out about 1,400 kilometers above the surface. So we see the haze there. Now, there have been some it's very difficult to measure the composition of the haze. The haze is very complicated. So one way to study that is to actually reproduce what's happening in Titan in a lab. And this has been done by people at LPL. A student, Sarah Horst, did her PhD on this, working with French, working with Roger Yell, who's another professor here. And basically, they simulated the chemistry, the breaking up of the methane, the breaking up of the nitrogen. And what they found as a byproduct was amazing, and that they found 5 nucleotide bases, and they also found amino acids in there. So that suggests that maybe part of the haze is made up of the building blocks of life. Okay, so this chemistry is going out at a pretty rapid rate from geological time periods, because it would take, if we just take the atmosphere now on Titan and we didn't add any more methane to the surface or any more methane to the atmosphere, then in 20 million years, the atmosphere would be devoid of methane, be devoid of all of the products of methane, and you would only have a nitrogen atmosphere, which has very little greenhouse, and so the atmosphere would shrink, it would become cold, and it would basically largely freeze on the surface. So you have to somehow supply the methane very rapidly to Titan's surface, and we don't know how to do that. So the thing to learn here is that the haze is very, very interesting, but we don't really know what's keeping the methane in the atmosphere, why methane has an atmosphere in the first place. So let's look at the amount of methane that's in the atmosphere, look at the humidity. And when we talk about humidity on Titan, we mean the humidity of methane, because methane is basically playing the role that water plays on Earth. And so if we just take, this is just the humidity over the airport in Tucson. And you just take some odd day, any day you want to, and it's a mess. You can see that it changes. And this is taken a few it's like a day apart at a certain time of the day. And it just changes a lot. Now, if you look at Titan, it's not a mess. What happens is you find out that the humidity, or the mixing ratio is constant from here to here. The humidity increases. Now, the humidity increases only because the temperature is going down as you go from here. But basically, the methane is the same mixing ratio from here to about here, and then it just follows saturation. So it's saturated here, and it doesn't. And we've only got one measurement of this, but I would bet that this is what it looks like everywhere on Titan, essentially. The reason is because it's just so elegant, right? It basically tells you that there's methane on the surface, and that methane is just mixed up to about 7 kilometers, and then above that, it just saturates over here. So it's very, very elegant, and I'll try to convince you of that with the next slide. Here's a question for everyone. If you actually know the answer, don't say anything. But okay, what if, here it is, what if you take all the water on Earth and you just make it into a layer, a uniform layer on Earth? What would the depth of that uniform layer be? And so, okay, how many of you, let's do hands just so that you can stay awake a little bit. So how many of you think it's 10 kilometers and below?
This is just the water that's in the atmosphere or all the water?
This is the water in the ocean. Mm-hmm. Yeah, good point. So this is the first one. So how many would think it'd be like 10 kilometers or lower? Okay, 10 kilometers. Okay, what about 10 to 50 kilometers?
50 or 50?
10 to 50. So I'm advancing it quite a bit. 10 to 50. Okay. Okay. The answer is that it's 3 kilometers. 3 kilometers. So there's 3 kilometers. If you took all the ocean, you get 3 kilometers. Now let's do it for the amount of water in the atmosphere. Okay. So what about, so there might be a little less. So let's start with a centimeter or below. 10 centimeters or below. 30 centimeters and below. A meter. It's 3 centimeters. So there's a lot of, there's hardly any. And see, this is the idea. Look, Kitty. There's Kitty. Wait. So the amount of surface liquid needed to saturate the atmosphere is about a centimeter. Say you have 50% humidity in your atmosphere. You want to saturate it, so you want to just load it with all the water you can. Then you would need to evaporate a centimeter of water. It's hardly anything, right? It's like this much water you'd have to evaporate. That happens easily here in Tucson. Now, if you consider Titan, Titan has a very situation. So here's the Earth's surface, how much water there is in the ocean. Here's how much water there is on the surface due to the atmosphere. And here's, wait, what's going on? What did I do over here? I expect to put Earth. Okay, forget that. I didn't say anything. So, for Titan, Titan's atmosphere has 5 meters, the equivalent of 5 meters of methane, as opposed to Earth that has 2.5 centimeters. Now, Titan has 1 to 2 meters of methane on the surface. So this is the amount in the lakes. If you take all the lakes on Titan and you just spread it uniformly, you would have 1 to 2 meters across the globe of Titan. And in contrast, you have a very different situation here with the atmosphere. So basically, Titan is a vapor planet. It doesn't really have very much methane on the surface, just a tiny bit. And Earth has all of its water basically in the oceans, hardly any of it in the atmosphere. So it's very, very easy for Earth to change its humidity. It occurs very easy. You just have to evaporate a centimeter. If you're starting at 50% humidity, which is good average, you just have to evaporate a centimeter. Whereas on Titan, if you want to increase the humidity by 50%, you have to evaporate 8 feet of methane. So I'm giving you an idea of what 8 feet of methane is. That's actually what I used to do in Hawaii quite a bit. But so the methane profile in Titan doesn't change. It just stays that way. Okay. Okay, we're still stuck with this thing. Okay, so the methane humidity doesn't change because methane is in the atmosphere already, right? But we're still stuck with this thing. Where does the methane come from? So there are 2 clues. One clue is that I forgot to mention that the question is, why are the lakes at the poles? And the reason why the lakes are at the poles is that the circulation goes pole to pole. And essentially, if you take any model of Titan, and there's a lot of GCM models of Titan, it's about 10 different groups doing GCM models of Titan. They all assume something different, but every single model that they do, if you put some methane at the tropics and you let your code run, all of them with different assumptions, because then you find out that the methane evaporates very quickly, it just moves to the pole. So it just goes to the pole. So we pretty much understand why the lakes are at the pole. They're in the pole because if you put it because of the circulation, essentially. Circulation evaporates the stuff in the tropics and it moves to the pole. But we found one place where there appears to be a lake at the tropics at minus 11 south latitude. And it's been there for a decade. And so it should have evaporated. It should have evaporated. So that's one clue. The other clue is that when Huygens landed, it landed with a puff. A puff of methane came out. Here you can see. the calculation. This is the Huygens coming in, descending, and it's getting more and more methane, as it should, because the density is increasing, getting more and more, and then when it hits the surface, the methane shoots up. The nitrogen does not shoot up, only the methane shoots up. And that's suggesting that there's a damp ground there, that it hit the ground and it's damp. And then there's another indication, and that is that, so I'm working right now on the first global composition map of Titan's surface. And what I'm finding is that there are very few places, it's this blue part, where you see exposed bedrock. Every place else, it's sediments, it's organic sediments. And all the dunes, and this is known from other studies, people have studied little regions right here, little regions right here. The dunes seem to suggest they're organics as well, which is consistent with what I'm finding here. But if you just take all the dune volume and you compare it to the haze that's coming down, and we do know it for the tropics because it's been measured by Huygens, then you find out that we have a lot of organics here, and we have just the amount of organics that we would expect if the atmosphere has been going for 4.5 billion years. So it's an old atmosphere, so it suggests that the atmosphere is old. And this suggests further, if it's an old atmosphere, but if the ethane is continually coming down in the old atmosphere, we should have like half a kilometer of ethane. Where did the ethane go? Well, the suggestion then would be that maybe it's porous and maybe it's going into aquifers, because we have that problem that we don't see the ethane. And people have been coming up with a lot of exotic ways of hiding the ethane, given that we have all these organics on the surface, which suggests that it's an atmosphere that's been producing organics for basically 1 billion years. So I'd like to end with this thought. It's just a thought. Is Titan an oasis planet? So is it a planet that actually has this methane cycle, and the methane is actually in contact with subaquifers underneath the surface that are feeding the methane, and also taking in the organics, taking in the ethane, and things like that? And if so, and since water is liquid once you get down to a certain level, I mean, it may be at 3 kilometers, it may be really too deep, could you get a situation where you have liquid water plus these organics, plus these amino acids kind of mingling around, making some kind of chemistry that might approximate something interesting? So I'll end there.
Questions? We've got a microphone. Let's see. Yeah. Over here. Right. Microphone coming.
Okay. So in your presentation, you never really mentioned why is Titan the methane oasis planet? Why didn't this happen to Callisto or Ganymede if they share very similar masses and relative location in the solar system?
Well, that's a very good question. The short answer is we don't know, okay? But I can give you long answers because, we've all been looking at it, trying to figure out different ways. So one thing that I've done to ask that question, because it bothers me too, is say, well, okay, Jupiter's bigger than Saturn. And so anything that comes in that's attracted to Jupiter is going to come in and hit the moons very, very hard, very fast. And so Saturn's is not as massive, so the velocity at which things come in and beat at the satellites is going to be slower. So it's going to be easier if you have an atmosphere to retain it for Titan than for Jupiter. But the problem with that study is that you don't really know how big the planetesimals were that were hitting things. That's a common problem. And so we could scale it from the moon, we could scale it from other satellites and things like that, but we really don't know. So it's interesting. But the other answer would be that the Jupiter is closer to the sun, so the chemistry is different in the solar nebula. So maybe the chemistry of the solar nebula was enough different that you would get basically a different composition. Another thing is, this is the last one, I'll only do three. The other thing is that Titan is in an elliptical orbit. So then the question is, well, what's it doing in an elliptical orbit? And so there's one study that says, okay, probably what's happening is it used to be in a more elliptical orbit, and it's now dampening down. Why is it just dampening down now? Well, because maybe there's ammonia that's acting as an antifreeze. It's damping now. It's damping down now, and as it damps down, it twitches. It basically causes, it experiences a different gravity field, and that causes it to flex. And maybe that caused the atmosphere that exists here. So there's all these ideas, but we really can't get a handle on it. That's why I say we don't really know.
Other questions?
Thank you. So back with the P, U, and T with the atmospheres and such, if I'm looking at Titan as far as like microbiology, I just want to kind of understand if the pressures are the same, does the U being 10 times greater, does that turn me off at all at looking at Titan as a prospect for maybe being life on there?
No. And the reason why is because, okay, the U is big. That's only because the gravity is small. And so to get the same pressure on Titan, you need to have a lot of gas, essentially, above it. But it's more, you're more interested in the ambient conditions. So the ambient conditions, the pressure is great. Now the temperature is very, very cold. And so that would be an issue. And in terms of, and then there isn't liquid water on the surface. So you have to go down deep into Titan to get to liquid water, where it's warmer.
Thank you.
Okay, so you mentioned at the beginning that Titan has an atmosphere. I'm not sure if I missed it, but does that mean it has a magnetic field like Earth, or how is it able to maintain that atmosphere?
Oh, yeah, the magnetic field. Does it have a magnetic field? I'm trying. Does anyone here know? I don't think it does. That's my thoughts, but I'm not quite sure. I'm not quite sure. It does have a magnetic field, and that it does react with the
But how does it keep its atmosphere was the question.
how does it keep its atmosphere?
Yeah, so because I know Earth, the way it helps maintain the atmosphere is with the magnetic field.
Oh, okay, yeah.
So how does Titan do it?
Yeah. Okay, for Titan, basically it keeps its atmosphere because the molecules in the atmosphere are very big. So methane is big, and nitrogen is big. Now, part of the atmosphere is always escaping because when the methane breaks up, it releases hydrogen, and hydrogen cannot be held on by the gravitational force of Titan. So that's why it's an irreversible process. So when you have methane, you make these radicals, and you never can go back to methane because you're always losing the hydrogen. But basically, the answer to your question is that the molecules are really big, and so they just hold on through the gravity.
Other questions? Back here.
So this isn't so much about Titan, but the Cassini mission. I know it was between NASA and the European Space Agency. Is there any reason that NASA didn't complete the mission alone? Like why they needed it to be a joint mission between both of them?
It's very expensive. I mean, it really is very expensive. But that's actually an interesting question because right now we're not collaborating. Largely because, or not collaborating very, very much. And that's because we have very strong laws about what we can ship out and how we ship out technology. And And so, but it's always better to have a large group of people helping out. First of all, the ideas are, you get much better synthesis of ideas. And it really surprises me how, even though I work a lot with the French, and I actually did most of my PhD in France, I speak French, I still don't quite know what they're doing scientifically. I mean, yeah, I still don't understand these guys, no. But I still don't understand always what they're doing until, much later. So so you just get more ideas. But the money is very important. We're trying to do this in some of the spacecrafts that are currently being designed. But we'll see.
Any more questions? Okay, one last question up there. The last one.
So you said Titan's atmosphere was hydrogen based. What else does it contain besides hydrogen?
What other molecules
Right.
and things? Yeah. Well, the odd thing is that basically almost the entire atmosphere is predicated on methane and nitrogen breaking up. The only exception of that is the oxygen that's coming in through meteorites. But basically, it's methane that runs the show, with nitrogen as well. So there's a lot. I mean, I just mentioned a lot, but there's just tables and tables and tables of all these different organic things that are basically the byproducts of this photochemistry.
Okay, let's thank Caitlin one more time.